We already talked a lot about, in one-dimensional finite difference time domain, how to calculate transmittance and reflectance. Things are a little bit more complicated when we go into 2 dimensions because waves can be traveling at different angles when it hits our transmission and reflection points where we're recording that. And there's also some additional things that we have to consider in terms of where we place the PML relative to our device. So we're going to talk about all that in this lecture. We'll certainly review what we did last lecture. And as I mentioned, there's 2 ways to calculate how much power is reflected or transmitted through a device. There's the easy way and the hard way. The easy way is just integrating the pointing vector at the top and the bottom of your grids. But of course, that's not the way we're going to do it in this class. We're going to do it the harder way. And the reason we're doing that is because there's more information in it and there's more things we can do. We learned last lecture that when a wave hits something that's periodic, it actually diffracts into discrete modes. So our approach, we're going to calculate how much power ends up in each of those separate modes, and then we simply add up all of the reflected diffracted orders to calculate the overall reflectance, and we add up all the transmitted diffractive orders to calculate the overall transmittance. So that's how we'll do it. And also, we need to talk about that we need to place the PML at some distance away from our device, and I want to put some theory behind that to explain why that is. So last time, we started off by introducing the wave vector, and the wave vector carries 2 pieces of information. It points in the direction the wave is moving, so if we look at our wave fronts, that k vector is perpendicular to the wave fronts. And the magnitude of that is 2 pi divided by the period of the wave. Now, if we know the frequency of the wave, then the free space wavelength is fixed. And in that case, we can actually think of more of the magnitude of k as conveying refractive index n, because 2 pi over the free space wavelength is a constant, and so the magnitude more conveys n in that case. But overall, wave vector, 2 pieces of information, the direction of the wave and 2 pi divided by the period. The wave vector can be a complex number. When it is purely real, we're talking about a pure oscillation without any decay or anything. When that wave vector is purely imaginary, we're talking about pure decay, like the evanescent field outside of a waveguide. But in general, most of the time, it's complex, meaning it oscillates and it decays, both at the same time. And in fact, these are the only 3 things that an electromagnetic field can do, because the solution to the wave equation is complex exponentials, and those are the only 3 things that complex exponentials can do. Let's think about these evanescent fields in 2 dimensions. And we have 3 examples. We'll start at the far left, and we have the interface between something with a low refractive index and the wave goes into something with a high refractive index. I know it has a lower refractive index up here because the wavefront is more stretched out. It's traveling faster, so it has a longer period. Down here it travels slower, the wave, so the wavefronts become compressed. And this little gray plane here, that's highlighting the interface. The fields on both sides of this interface must look the same. That's boundary conditions. And so the angle of this wave, since it has a different period than up here, the angle of this has to be the same such that the cross-section at the interface makes the fields look exactly the same on either side. So that describes refraction. Let's reverse this. Let's have our wave go from something with a high refractive index into something with a low refractive index. Again, we know this is a higher refractive index because our wave fronts are compressed. Down here they're stretched out. But also, boundary conditions requires the fields look the same on either side of the interface. So these 2, since they have different periods, they have to be angled differently such that this cross-section, they look the same on either side. Now, we're coming in at even a larger angle. And if we look at the field variation at that interface, it turns out it's varying more rapidly than can be supported down here. If we look at the wavelength between these 2 humps, it's actually smaller than the two humps that would be supported here. So we can't support a propagating wave here. It's just varying too rapidly. And we say that it's cut off, and we get this evanescent field that extends away. So even though we're going to get total internal reflection here, that wavefront does temporarily penetrate that interface into some depth, maybe a wavelength. The closer we are to that cutoff or the critical angle, the longer or the larger that evanescent field. As we move away from it, that evanescent field gets smaller and smaller and also varies more abruptly as we come in at a larger angle. So the point is, we can have waves cut off in certain materials, and that doesn't mean that those types of waves can't exist in those materials. It just means that they're cut off and they become evanescent and they decay. Then we talked about fields in periodic structures, and we said a field or a wave traveling through something that is periodic, the amplitude of that wave takes on the same symmetry as the periodic thing that it's in. And that makes intuitive sense really from this picture. Then we said, okay, so the periodic structure chops up the wavefront, it makes the wavefront periodic with the same symmetry. Well, we know that anything periodic we can decompose into a complex Fourier series, so we did that. But now our field is being represented as a sum of discrete things, and those discrete things have the mathematical form of plane waves. So in fact, anytime our field becomes periodic, we can think of that periodic field as a bunch of plane waves all at different angles, and we just adjust their amplitudes and angles so that when they all overlap, we would reconstruct this original periodic electric field. So this set of plane waves is what we call the plane wave spectrum. And in fact, we could go into the lab, we could set up a bunch of horn antennas at different angles, and we could aim them at some region of space, and where all those beams overlap, we really could construct any type of periodic field that we wanted to. So a wave comes into a grating, it's periodic. The act of the grating leads to an infinite expansion in the transverse wave vector component. So we have an incoming wave vector. The grating leads to this infinite series of transverse wave vectors. And notice as they go higher and higher order, they become larger and larger and larger. So we phase match each one of these into the grating region. And what we see is at first they're small enough that they correspond to waves traveling at different angles. But at some point, this wave vector becomes so large, it's describing a field varying too rapidly to be supported as a wave within the grating. And it is cut off, and it's evanescent. And we see the field trapped at the surface, varying very rapidly, more rapidly than can support a plane wave, but it's there and it penetrates. And as we go larger and larger, we're talking about even faster and more rapid variations. The evanescent fields are trapped even tighter to the surface, and so on. And this happens for positive and negative orders. So the other thing we mentioned is that usually only the lower order set of these transverse wave vectors correspond to propagating waves. The rest are cut off. So in fact, the vast majority of these really are evanescent fields. We still call it the plane wave spectrum. Maybe we should call it the evanescent wave spectrum. But we still call it the plane wave spectrum, and only the lower order few are plane waves. Okay, so now we're going to step through the easy way of calculating transmission and reflection from a device. Not all the details you'll need to implement it are here. I just want to give you a taste of what happens here. So remember, instantaneously, E cross H gives us a pointing vector that tells us the flow of power, but that's an instantaneous thing. What we need to do on our two-dimensional grid is integrate that pointing vector across the complete top and the complete bottom of our grid. And that gives us a total power flow. So we'll do this integral twice. It gives us a total power flow leaving the device, one on the reflection side, one on the transmission side. For a two-dimensional grid, this really, I should only be showing a single integral here because we're only integrating across one dimension. If we had a three-dimensional grid, we would have a double summation here because the cross section through that grid at the top and the bottom would be a plane, and we need to do a double integration across that. So that's really the most generic formula. For a two-dimensional grid, it's only a single integral. So if we know the Poynting vector by E cross H at the top and bottom of our grid, we need to look at the components. It turns out this transverse component of the Poynting vector, if here's our device, it's carrying power horizontally. This is not power leaving the device. It's only the Z component of the Poynting vector on the reflection and transmission side that contributes to carrying power to or from the device. So for calculating transmission and reflection, it's only the Z component here, or the vertical component of the Poynting vector, that we listen to. We want to ignore the other components. So let's take the cross product. We have the Poynting vector is E cross H. We expand that out. Remember, we only want to listen to the Z component. We're defining that as being the vertical direction. That's the one that transports energy to and from the device. These other components only carry power within the device. They don't contribute to moving it away. So we'll just go with the Z component here. And we can interpret those differently. The first component is talking about power flowing in the positive Z direction, and the other component is talking about power flowing in the negative Z direction. So at the top of our grid on the reflection side of the device, it's really this one that we'll listen to. We should not even have this component. There should not be any power flowing in the positive direction if we've done our total field scatter field correctly. Likewise, on the transmitted side, since we don't have a source at the far side of the grid propagating backwards, this should be negligible, 0, and we're only going to listen to this component. But in general, we can have power flowing both ways, and we can differentiate those with this equation. So in our two-dimensional setting, we're formulating our code based on the EZ mode. That means there will be no X component. There's no X component of the electric field. So this term's gone. We're only talking about this term. That's the only one we need. And in our two-dimensional grid, it's the Y direction, which is vertical. So in this case, we listen to the Y component of the Poynting vector. There is no propagation in the Z component. We ignore that. And the X component is having power go horizontally within the device. So we ignore that. And so our Poynting vector for our EZ mode is essentially just EZ times HX. Now, one thing we need to be cautious about when we implement this, EZ and HX exist at physically different points within the Yi cell. We have to interpolate those to a common point before the product of the two makes any sense. We'll get slight errors if we don't do that. So we interpolate those to a common point, multiply them, and then we know the Y component of the Poynting vector within that cell. Okay, so on to the actual way that we are going to calculate transmission and reflection, and that's by the plane wave spectrum. We will calculate how much power is in each of those diffraction orders on the reflected and transmitted side, and then we'll add them all up. So again, we start with the Poynting vector, and we start with the instantaneous Poynting vector, which is just E cross H. Really, we're interested in the RMS power flow, which is a frequency domain concept. And that's 1/2 times the real component of E cross H in the frequency domain, where we take the complex conjugate of one of them. We'll take the complex conjugate of H. So that's how we calculate power from phasor quantities. So rather than keep writing this parenthesis R and omega, we'll just write our Poynting vector this way. So 1/2, the real part of E cross H, and we're taking the complex conjugate of H. So we're flipping the sign on any imaginary component of that. Now, in linear, homogeneous, isotropic materials, E and H will be at 90 degrees with respect to each other, and both of these will be at 90 degrees with respect to the Poynting vector and the wave vector K. So the wave vector and the Poynting vector are collinear. They are parallel and in the same directions. Now their magnitudes are different because they're conveying different information, but they're in the same direction. So if we construct a unit vector from either one of those, that should be the same thing. So the pointing vector divided by the magnitude of the pointing vector gives us a unit vector in that direction. So also k over the magnitude of k gives us a unit vector in that direction. And since they're the same direction, these two unit vectors now have to be equal. So we can use this in our equation. So we have pointing vector 1/2 real part E cross H. We need to know what to do with this cross product. Well, knowing that E and H are orthogonal to each other, we know immediately what the magnitude of that is. It's just the product of their magnitudes. If these were at some angle with respect to each other other than 90 degrees, we'd have a sine or a cosine term in here to make this smaller. But knowing these are at 90 degrees, that's when the cross product is maximum. The magnitude of that cross product is E cross H. We also know that the cross product gives us a vector in a direction orthogonal to both of these. We already know, because we're in an LHI material, what that direction is. It's K or P. It's either the wave vector or the pointing vector. We can use either one. So let's just take K divided by the magnitude of K. That will be the direction of our cross product. Now we know the magnitude and direction, so we can replace our cross product with the magnitude and the direction. Next step, let's eliminate the magnetic field. And why are we doing that? Well, if we're modeling the EZ mode, it turns out all the information we need is really just in that EZ component. Now, for that HZ mode, that would be opposite. All the information will be contained in the HZ component, and in fact, we'd want to eliminate the electric field for that case. But here we're going to be analyzing the EZ mode, so we want to eliminate the magnetic field from our pointing vector equation. So now we look at the material impedance, which is sort of like Ohm's law. And it says, given a plane wave traveling through an LHI material, the magnitude of the electric field divided by the magnitude of the H field is the impedance of that material that the plane wave is in. Well, we just solve this equation for H, and we replace the H down in this equation, and we end up with E squared over impedance. That will be the magnitude of our cross product, and we also still have the direction of the cross product. So we've eliminated H. We have it completely in terms of the electric field. Let's remind ourselves again, it's this vertical component, and in this case I'm showing the Z component, that's carrying power away from the device. So we only want to listen to the Z component of the pointing vector, at least in terms of calculating transmissions and reflection. So we only want the Z component here, so how do we do that? Well, we take this vector K and just use the Z component of it. Otherwise, the equation remains unchanged. So this is just the Z component now of the pointing vector, or the vertical component. That's what transports power to and from the device. Let's rewind the clock a little bit and remind ourselves the electric field is periodic. We're going to have periodic boundary conditions on the left and right of our grid, PMLs at the top and the bottom. Our electric field will be periodic. We can decompose that into a complex Fourier series. So we have this Z component of the pointing vector equation. How do we write this in terms of our S's? Well, in fact, it's really the same thing, except we have a Z component of the pointing vector for each of our diffracted modes M. We're essentially taking this summation for E, plugging it in down here, and noticing we have a different pointing vector for each diffraction order. So the Z component of the mth diffracted order is simply 1/2 the real component of the KZ component for the mth diffractive order divided by the K vector for the mth diffracted order times the amplitude of the mth diffracted order, of course absolute value squared, divided by the impedance. And the impedance is the same for all the different modes because they're all in the same material. So now we have a Z component for all of our different diffraction orders. Let's think about the power in our applied wave. So we have some source wave and it has a pointing vector potentially pointing at some angle. But remember, it's only the Z component we care about. It's only the component vertical to the device that will be carrying power toward our device. So the Z component of our source wave is our same expression here, except we'll write an ints here to remind us this is the z component of the incident wave, the magnitude of the wave vector of the incident wave. Here's the amplitude of that wave, the incident wave, and the impedance in the region where the incident wave is. So that tells us how much power our incident wave is bringing to our device. Now we're going to define something called a diffraction efficiency. We know that this applied wave comes in, hits a periodic structure, and that splits up into a bunch of discrete modes. Well, the power from that applied wave gets distributed amongst all of those different modes. So the fraction of power that comes from that applied wave into each of those diffraction modes is called the diffraction efficiency. I actually don't like that title because when we give it a name like efficiency, that implies we always want that to be a big number, and that's not the case. Sometimes we want them small, sometimes we want them big. But diffraction efficiency is defined how it is. It's just a fraction of power that ends up in the nth diffracted mode from the applied wave. So how do we calculate? How do we calculate the diffraction efficiency of the nth diffracted order? Well, we know the z component of the applied wave, and we'll calculate the z component of the Poynting vector of the nth diffraction order, and if we divide those two, we get that fraction of power from the applied wave into that diffraction order. Well, if we add up the diffraction efficiencies of all of the reflected modes, we will get the overall reflectance. If we add up all of the diffraction efficiencies of the transmitted diffraction orders, we get the overall transmittance. And if we add these two together, we should get all of our energy back. And that assumes we did not include loss or gain in our model, which we absolutely can do. But if we don't do that, we should get 100% back. In fact, even if I am incorporating loss or gain into my model, I won't do that at first. I will turn that off and make sure that all my energy is accounted for. Because if I don't have loss or gain, I run my simulation and I see that my conservation of power is down, I add reflectance and transmittance and I get 70%. 30% of my power is unaccounted for. Clearly there's something wrong. And we already sort of know from some of the simulations we saw that could be that there's still energy stuck in the model. It could be that the field is too close to our PML. We'll talk more about that. It's a sign that there's a problem. So we should always get conservation at 100% all the way across our frequency spectrum. It's a very, very good self-check. Now, if we did include loss, clearly that conservation would dip down below 100%. And if there's gain, clearly it could come above 100%. If you have both loss and gain, it could do either or. So let's put all of this together. We start off with, we have the z component of the Poynting vector of our applied wave. We also have the z components of our reflected modes, the z components of our transmitted modes, and we have our definition of diffraction efficiency. So here's what we do. We define diffraction efficiency of the reflected modes as the z component of the Poynting vector of the reflected mode divided by the z component of the applied wave. Well, now we have expressions for these that we can substitute in, and we simplify down, and we end up with this expression. So this is exactly how we will calculate the diffraction efficiency of our modes. Now, analytically, we'll know our k components. From our model, we will determine the amplitudes of those diffracted modes. And we have a very, very similar equation for the transmitted diffraction orders. The K's and the mu's, that all happens analytically or before the simulation. It's our simulation that tells us the amplitudes of the transmitted modes. So those are the equations that we'll use. Now, we derive those equations based on knowing the electric field, that EZ component, if you will. If for some reason we had calculated the magnetic field components, we would have eliminated the electric field, but gone through the same exact procedure, and we end up, here's our equations for calculating diffraction efficiencies if we happen to know magnetic field quantities instead of electric field quantities. And if both are available to you, just pick one. They should give you the same answer. We certainly can't plug electric field quantities into the magnetic field equations. We'll have to pick one or the other. But if you know both, you're free to use either one and should get the same answer. So now I want to talk more about calculating power flow in FDTD. We'll provide the equations, but also how I visualize how the data is stored in the arrays. So here's the process. I guess I could have drawn a fancy looking block diagram, but I guess there's too much here and I typed it out. So step one, perform the simulation. And what you'll see on the transmitted and reflected side through the cross section, we need to do Fourier transforms there. And so we calculate the steady state field in those planes. We call them record points for one dimension. Here they're record planes. And so we calculate the Fourier transforms. And we do that for every frequency of interest. Once we're done the simulation, all we've done during the simulation is calculate the Fourier transforms. Once that's done, for every frequency we're interested in, we'll calculate all of the wave vector components of the diffraction orders or the spatial harmonics. We can do that analytically. We don't need any results from the simulation to do that. So in fact, we could have done that before the simulation, but we're doing it after here. Then we'll calculate the complex amplitudes of the spatial harmonics. Those are the S terms, or for the magnetic fields, those were the U terms. So we get that by looking at our steady state fields in the cross section and Fourier transforming them. But instead of Fourier transforming frequency to time, we're Fourier transforming from space, the X coordinate, into our plane wave spectrum, if you will. Once we have those complex amplitudes, we have all the information we need. We calculate the diffraction efficiencies of all of our different spatial harmonics. That means all the different diffraction orders. Once we know all of those, we can add all of the reflected diffraction orders and get the overall reflectance. We can add up all of the transmitted diffractive orders and get the overall transmittance. And then, of course, we can add those together and look for energy conservation. And if loss and gain is turned off, we should get 100% of our energy back. And that's a great self-check, and it's something that you should always do if you have that information available to you. Okay, so here's step one and how I'm envisioning the grid. We still have yet to talk about why there needs to be space between the device and the PML. We'll get to that. But let's just say there has to be that space. So that means we'll have some plane where we're injecting our source. This is our one-way source. So from this line down is really the total field, and above here is the scattered field. So we'll have a plane, cuts a complete cross-section through the grid. We'll call that our reflection record plane, and we'll be calculating Fourier transforms at each one of these points for each frequency of interest. And we'll also have a transmission record plane. And then, of course, on the outside of the record planes, we have our PMLs absorbing the outgoing waves. And on the left and right, we're using periodic boundary conditions to model a periodic structure. So that's what happens. That's how we set up our grid, and we perform this FDTD simulation. This is how I envision the same grid, but in 3 dimensions. So we have some crazy device in here. We still have some source plane where we're injecting a one-way source. We have our reflection plane, and then outside a reflection record plane. Here it's actually a 2-dimensional plane. Our PML, we have a transmission record plane and another PML. Here we would be using periodic boundary conditions at the X and Y boundaries and PMLs only at the Z-axis boundaries. Now during the simulation, we are calculating Fourier transforms across our grid for every frequency of interest. So for example, for frequency 1, whatever size this array is across the grid, we'll have one of these, and we Fourier transform each point at frequency 1. We also Fourier transform these same fields at the same location, but stored in a second array at frequency 2. We'll Fourier transform these same fields from these same points at our third and a third array at this third frequency, and so on. So every frequency we're interested in, we essentially duplicate this row through our grid and store the Fourier transforms. And we'll be calculating these, just like we learned in one-dimensional finite difference time domain, we'll be calculating these as the simulation is running. We do a similar thing on the transmitted side. So we'll take this array and Fourier transform the fields at frequency 1, 2, 3, all the way up to however many frequencies we're interested in. Very often this is 100 or 200 different frequencies, so we can create a nice smooth transmission and reflection plot. So if our grid is 20 cells wide and we're interested in 100 frequencies, we will have an array where we store this data that will be 20 points by 100 frequencies. There'll be 2,000 data points in here, and then another 2,000 for the transmitted side. So these arrays on the right is how I'm envisioning these being stored in memory. Now the simulation is over. We have all those Fourier transforms. We have our steady state fields. Now if we had used a frequency domain code, let's say finite difference frequency domain, those arrays would be our answers for each frequency. We would get the same information whether we used a frequency or time domain code now. Okay, so now for every frequency of interest, we're going to calculate the wave vector components associated with all the diffraction orders. We have to repeat this for every frequency that we're interested in. So we have a grading vector, which is really talking about the periodicity horizontally here. That's just 2 pi divided by the period. Our infinite expansion of transverse wave vector components is just minus m times this grading vector. Or think of it as being 2 pi m over lambda x. And this m, in theory, goes from minus infinity to positive infinity. There's always an infinite number of diffraction orders. However, the fact that we've chosen a grid and we have some limitations in resolution, we can only resolve so many. So let's just say we have 11 points across in our grid. This m will go from minus 5 through 0 up to positive 5, so there'll be 11 numbers here. So for that reason, it's easiest to make the width of our grid an odd number of points. It's not necessary, and we can pretty easily fix that, but for simplicity, we'll always make the width of our grid an odd number of points, and that ensures that our diffraction modes always have symmetry. So if we have 21 points across our grid, this m array will go from minus 10 up to positive 10, passing through 0, so that will be 21 different points. So we get a set of 21 different transverse wave vector components. So we're storing that in an array that is the same size as the width of our grid. This grading vector component is just a single number. So given this, now we're going to calculate the longitudinal components. We could potentially have different materials above and below the device, so in fact we'll calculate these longitudinal components separately for the reflection region, which is above the device, and the transmission region, which is below the device. So we go back to our dispersion relations and we calculate the longitudinal components. Again, they're stored in an array that's the same size as the width of the grid. We calculate these from our kx. So we end up with 2 more arrays. And I'll remind you one more time, we'll need one of these for every frequency that we're interested in. So you can imagine doing these calculations in a big loop that's looping over frequency. And the first step inside that loop is to calculate all the wave vector components associated with your diffraction modes. Both the reflected and transmitted sides share the same transverse component, but they have different longitudinal components. And these, because we have a square root of a difference here, can be real or imaginary. Then what we've done, we look at our Fourier transforms that we've done, where we look at our steady state field. So now we know what the field looks like in the cross section of the grid. We do an FFT on those. And when we FFT from the width of our grid, we get another array, which are the amplitudes of our diffraction orders. So we go grab that array, which is our steady state field in the cross section. We FFT that data, and what we end up with is an array of that same size. We have 21 points across the grid. We end up with 21 numbers, those 21 numbers will be the amplitudes of our diffraction orders, or the amplitudes of the plane waves in our plane wave spectrum. So once we know those amplitudes by FFTing our steady state fields, now we know everything for our diffraction efficiency calculations. We just calculated all the wave vector components. Just through our FFT, we know the amplitudes of our diffraction orders, and we also know the amplitude of our applied wave. Normally we just make this 1, and sometimes we don't even write it in the equation. But if it is something other than 1, then we need to include that here. And so we do the same thing for the reflection and transmitted side. So now we know the fractions of power in our reflected modes and the fractions of power in our transmitted modes. And we call those diffraction efficiencies. Once we've calculated the diffraction efficiencies for all the reflection diffraction orders and transmission diffraction orders, we simply just add up all of the diffraction efficiencies for the reflected modes. Add it all up, we get a single number now, 1 for each frequency. We do the same thing for the transmitted modes, and we get a single number, but 1 for each frequency. And we have overall reflectance and transmittance. Now we should be able to add those together and get conservation of energy. And that's the very last thing we do. So anytime you calculate transmission and reflection, it's always good practice to add those together and make sure you have 100% or something very close to it. Typically you'll see 99.8 or 100.05% type numbers. Those are acceptable. But if you end up with 110% or 60%, something is clearly wrong, and that's a sign that either energy is still stuck in the model, your grid resolution's too poor, or any number of things that we've already talked about. So here's a summary of how I visualize all the different arrays. So we have our grid where we're doing our simulation. We have our cross section through the grid where we're looking at or we're calculating the reflection from our device, and we also have the plane where we're looking at the transmission through our device. So as we're simulating, we're storing a big array in memory. It's the width of our grid, but the height of this array is the number of frequencies that we're interested in. And we're Fourier transforming the cross-section of this grid. Every single point we're Fourier transforming for frequency 1, we're Fourier transforming at frequency 2, we're Fourier transforming at frequency 3, and so on. And we do the exact same thing on the transmitted side. We store an array that is the width of our grid, and the height of that array is the number of frequencies. Once the simulation is over, we'll take each row and FFT it, and now we know the amplitudes of our diffracted modes. And we do it for the reflected and the transmitted side. At this point, we calculate our diffraction efficiencies. And when we do that, we notice that it's only the ones that correspond to plane waves that we count here, because they're the only ones that can carry power away from our device. And so it's only these lower order few that actually contribute to that. And these other ones are evanescent and cut off. We tend to ignore them in our equations. And the part that ignores that is this real thing. And what that is doing is it's any k vector that is imaginary, we end up ignoring it. So it's only the purely real ones corresponding to plane waves that count towards a diffraction efficiency. It's usually just the lower order ones. So all we've done is do our diffraction efficiency calculations. Then for every row or frequency of interest, we just add all of these up, and we get the overall reflectance at frequency 1. We'll go to the second row, add all these up. We'll get our overall reflectance at frequency 2. We do it for all of the different rows, and we get all of our reflectances. We do the exact same thing on the transmitted side. We get all of our transmissions. And then we have two 1D arrays that we can plot, and we will see transmission and reflection as a function of frequency. So here's another sort of procedure for doing this that includes the equations. So the first step is perform the simulation, and at every frequency and point of interest, we're calculating a Fourier transform as the simulation is running. We're also Fourier transforming the source. Once that's done, in the post-processing step, this is what we need to do. We'll calculate the incident wave vector. Then we calculate all of the wave vector components. Remember, this is happening for each frequency of interest. We calculate all of the transverse wave vector components, and those are the same for both the reflected and transmitted fields. Step 4, now we calculate the longitudinal components. Now those can potentially be different for the reflected and transmitted modes because there might be a different material on the top or the bottom of the grid. And since we calculate those from the dispersion relation, they can potentially be different. Then we normalize our steady state fields according to the source. So we know that the power content in our source dips as frequency goes down if we've used a Gaussian source. And so we need to remove that artifact from our Fourier transformings by dividing by the Fourier transform of the source. Now we have all the information to calculate the amplitudes of our diffraction orders, and we just FFT those steady state fields in the cross section. Then we feed all this information into our diffraction efficiency calculations, and notice in these equations we're not dividing by the amplitude of our source wave squared because we're going to assume that that's just 1, and I mentioned before sometimes we don't even write it here. So we have a unit amplitude source. And how are we doing the unit amplitude source? It's when we divide by the source spectrum that essentially makes it as if we had just a unit amplitude source at all frequencies. So when we divide by the source, we remove that number here from these two equations. But after step 7, we know the diffraction efficiencies of all of the reflected and transmitted modes. Then the last step is we add up all of the diffraction efficiencies of the reflected modes to get overall reflectance. And we add up all the diffraction efficiencies of the transmitted modes to get overall transmittance, and we'll add those together to look for conservation. Remember, everything in yellow here we do for every frequency of interest, and normally that'll be 100, 200 different frequencies. So we do all of that work inside a loop that loops over frequency. When we're done, we'll have a one-dimensional array containing all of the reflection numbers, another one-dimensional array containing all the transmitted numbers, and we can plot those versus frequency and see a very typical transmission and reflection plot. So to bring it all together, here's the Matlab code for doing this. So the first thing we'll do is we'll initialize reflectance and transmittance in arrays. And how big do we make these? Well, this big N freq, that's the number of frequencies that we're calculating, and that could be 100 to 200. So we're making two arrays that have, let's say, 100 numbers in them. Then we set up our big loop that loops over frequency, and we do a lot of work for each one of these frequencies. So the first step is calculate all the wave vector component stuff. So since we're looping over frequency and we need wavelength for these calculations, we calculate the free space wavelength, which is the speed of light divided by frequency. Then we calculate the free space wave number, which is 2 pi over the free space wavelength. At this point, we can calculate the vertical component, if you will, of the applied wave vector, and that's just k naught times the refractive index where that wave is coming in, so that's on the reflection side. Then we calculate the array of indices of our diffraction order. So if our grid is 21 points wide, this array will go from -10 to +10, passing through 0, so it'll be 21 points. So that's just an array of integers. Then we can calculate the transverse components of our wave vectors, and this is common to both the reflected and transmitted side. That's just minus 2 pi m over the period, Sx. Then we calculate the longitudinal component for our wave vector. This was the transverse component. Then we calculate our longitudinal component, and that can be different on the reflected or transmitted side. So we have two of them, one for the reflected, one for the transmitted. And it's just square root of k naught times the refractive index on the reflected side squared minus kx squared, and then the square root of all that. And that could become an imaginary number. It could be real or imaginary. And then the same thing for the transmitted side. So at this point, we have all of our wave vector information. Then we move on to calculating reflectances. This EREF, this is where we've been storing our Fourier transforms during the simulation, and that's over the cross-section of the grid. So we'll take that and divide by our source, the Fourier transform of our source. So that normalizes it. Then we'll take ref and we'll do an FFT to it. And so what this is doing is calculating the amplitudes of our reflected diffraction orders. We follow this FFT with an FFT shift. That puts the zero order diffraction order in the center of that array. And we also divide by nx to have the amplitude make sense. Then we do our diffraction efficiency equation. And so here's the absolute value of the spatial harmonic amplitude squared times the real part of the vertical component of our reflection wave vector divided by the vertical component of the wave vector of the applied wave. So now ref is a little tiny array containing all the diffraction efficiencies of our reflected diffraction orders, and we add all of them up to get the overall reflectance at this particular frequency. We do the same thing on the transmitted side. We divide by the source, then we FFT it to get the amplitudes of the transmitted diffraction orders, then we do our diffraction efficiency equation. So now TRN comes out of this having all of the diffraction efficiencies of the transmitted modes, and then we add them all up to get the overall transmittance. And we store that overall transmittance at whatever frequency we're calculating. And we repeat this for all 100 or 200 frequencies that we're interested in. And then what I like to do at the very end is come up with conservation. I add reflectance and transmittance, and I'll always plot this along with reflectance and transmittance, and this is the number, assuming we don't have loss or gain in our model. That should be 100% all the way across. When that is not 100%, that's a sign something's wrong. We haven't run our simulation long enough, our device is too close to the PML, or something else is going wrong. So we model this. I'm including an example that you can calculate. You can calculate all the diffraction orders, and you can use this to benchmark your code and check the numbers. So here's the grading. We have a substrate that goes off to infinity. So we have a different material on the transmitted side than we have on the reflected side. We have just air up here. And here's all the different dielectric constants. So what we have the potential to have different dielectric constant here and here and here. But what we've made is this is just one monolithic device. The white is air and the gray is something else. But if we make an epsilon 1, a 2, an L, and an H, we can potentially just, with one code, just play with these numbers up front and be modeling different things. So the grading has some depth D. It has some period, in this case 1.5 centimeters. And we want to calculate all of the diffraction efficiencies at 10 gigahertz. So using a finite difference time domain code, here's the answers that I get. So we, of course, apply 100%. It turns out we only diffract into one mode, just our zero order mode in the reflected, and we get 18.6% in that. And we have 3 diffracted modes on the other side. And the zero order has a 51.1% diffraction efficiency, and the other 2 have 15.4. Notice those are the same numbers. This device has symmetry, so there has to be symmetry in the diffraction efficiencies. Well, I modeled this with a whole other technique, rigorous coupled wave analysis. This is actually a technique in the course that follows finite difference time domain called Computational Electromagnetics. We learned that one. And in principle, that is a much better method for modeling a device like this. It's much better suited for periodic dielectric structures. So, and a lot of times in the literature, they even refer to the answer coming from rigorous coupled wave analysis as being the exact solution. And it's not necessarily exact, but it is pretty darn good. And what we see is pretty good agreement between the numbers. Not exact, but pretty good agreement. So, if you have any desires to get any more accuracy than this, I'm not really sure how you would do it. FDTD and RCWA are both rigorous methods, and when they converge to slightly different answers. And this is something I think you'll just have to get used to in numerical modeling. I don't think it's possible to develop a numerical algorithm where there's approximations like finite differences and stuff like that in there, where we can get accuracy better than a fraction of a percent. We can converge and we can get precision with more digits, but is it really that accurate? I really doubt that. And even for more reasons, if we were to actually make this type of grading, well, these corners would probably be a bit rounded. You know, we're modeling this as square. Did we get the dimensions exactly correct? So there's other reasons. It's not even just numerical why your model may not match exactly what you've measured in the lab. But anyway, here's a good example that we can model in finite difference time domain, and we can check ourselves to make sure everything's working and we're calculating diffraction efficiencies correctly. So this is for a fixed frequency. We didn't sweep frequency here yet, but you can use this as a benchmark to make sure things are working. Okay, our last subject is PML placement, and we're armed now with everything we need to understand why we need space between our device and our PML. There's a crazy effect called electromagnetic tunneling, and whenever anybody talks about evanescent fields, they always say evanescent fields do not transport power or energy because they don't oscillate. So we look up here, this is what we talked about before. We have a wave going from something with a high refractive index into something with a low refractive index. It's coming in at an angle larger than the critical angle. So the spatial variance at that interface is too abrupt to match to a wave down here, and we get something that's evanescent. Notice there's no oscillations in the direction away from the interface, so it cannot be pushing power away from the interface. It does oscillate parallel to the interface, and in fact this evanescent field is pushing power, but it's horizontal to that interface. It's not pushing power away. So we commonly say that evanescent fields never contribute to power flow. There is one exception, and this is what's called electromagnetic tunneling, and this is exactly analogous to electron tunneling in semiconductors. Let's say we had a high refractive index material out here as a third material, and we bring it really, really close to this first material. We have this second material where, in principle, that wave is cut off. We see no oscillations here, but there's still a significant field amplitude. And when that touches this third material with a higher refractive index, which does support a wave, in this case it looks like I'm showing the same refractive indexes up here, suddenly we generate a propagating wave, and we're pushing power here. So in this case, this evanescent field is somehow contributing to the flow of power here, and that's called tunneling. And so in semiconductors, they also argue due to electron tunneling, there's only so thin of dielectrics that we can go until the electrons tunnel across that. So it's an exactly analogous thing. So there are times where these evanescent fields can contribute to power flow. So let's think about what's happening here. We have an interface, and here this is our total internal reflection. We have a wave coming in at pretty close to the critical angle. I know that because I see a large evanescent field. It's being reflected, and up here these dark and bright spots, what we're looking at is the interference between the applied wave and the reflected wave. But here's the interface, and clearly we're at probably 1 degree above the critical angle because we see very large evanescent fields. And so let's say this is our model, and we are calculating the reflected fields in this plane, and we're calculating our transmitted fields in this plane. Well, notice we're ignoring our evanescent fields here because the longitudinal component of the wave vectors of those evanescent fields are imaginary, and we're not counting those as power. However, those evanescent fields extend past our record plane, and if suddenly they touch the PML has a higher refractive index, they can suddenly couple into propagating plane waves. And so suddenly this electromagnetic energy essentially tunnels past our record planes. We're not counting it as power leaving our device, however, it certainly is. And so we can get violations in our conservation for those frequencies that have these large evanescent fields. So for this reason, we need space between our device and our PML to make sure those evanescent fields have a negligible amplitude before they touch the PML. I'll also mention there's been a lot of work in this to make PMLs better handle this case. And essentially what happens is we'll raise the refractive index to make it electrically longer before we incorporate the loss. So they look electrically larger, so in a sense it gives it more space for that evanescent field to decay before the loss is incorporated. And a bunch of other things, but we never in practice want those evanescent fields to touch our PML. I just want you aware that folks are working on this, and there's, in some cases, we can make it better, but it's always good practice to have space between your device and the PML so that evanescent fields won't touch it. We can always have our record planes slice through the evanescent field. That's not a problem. It ignores them just fine. We just don't want those evanescent fields to touch our PMLs. So how do we set up our grids? For example, how would we model this case where we're looking at total internal reflection at very near the cutoff? So this is the physics of our device, and here's how we would set up our grid. And we would put PMLs at the top and the bottom. So let's look at this evanescent field. Notice it decays, and at some point around here, I would say the amplitude is negligible. It never completely goes to zero, and we sort of have to make an engineering decision here of where it becomes negligible. And now we can start our PML without significantly affecting the answer to this. And so this is usually about a wavelength. There's some rules of thumb. If we have a non-resonant device that really don't have strong evanescent fields, we can usually make that about a quarter wavelength. So about a quarter wavelength space between our device and our PML. Now if we are sweeping frequency, that wavelength changes. So what we'll do is we'll go with the lowest frequency or the longest wavelength, and we'll make it a quarter wavelength for that worst case. And we won't change it each time. We'll keep it that way through our entire simulation. Now if a device is resonant, it does have evanescent fields, a better rule of thumb is to make that spacer region about a wavelength. Remember that wavelength will be the longest wavelength from the lowest frequency of interest. But we need to look at our simulations because there are circumstances where that's not enough. There is surface wave phenomena where that evanescent field can extend out dozens of wavelengths from the interface. So it's always best to be watching your simulations, looking at the fields, seeing what's happening, and looking at the conservation. And we can look at all this and we can tell pretty easily what's happening. So in the end, we've shown these before. We have a device in the middle of our grid. If we're modeling something periodic, like a diffraction grating, we'll have periodic boundary conditions on the left and the right. We'll have our PMLs at the top and the bottom. And we put about a wavelength space between our device and the PML. And our total field scatter field interface really can be anywhere. That doesn't really matter. We just need the space between the device and the PML. And we do want to record our reflected fields between the PML, but so below the PML and above the total field scatter field interface. So typically I'll leave one or two cells here between the PML and the total field scatter field interface where I record the reflected fields. And then we record the transmitted fields really anywhere here. I usually just, for whatever reason, put it right up against the PML, but not inside the PML. You would never want your record planes to be inside the PML because we've already started absorbing energy there, so your conservation will be off because of that. And a good place to start for the size of the PML is about 20 cells. And if we're modeling something that is not periodic, we need a PML all the way around, but we follow the same rules. We put about a wavelength between our device and the PML. We have our total field scatter field interface now, which is completely enclosing the device, and we still want to leave one or two cells between that total field scatter field interface and the PML because maybe we'll want to be recording the scattering from this device and maybe visualizing that in some way in terms of a pattern or lobes or whatever. But this is just an extension of what we talked about on the previous slide, just with PMLs all the way around. And still, I usually start off making the PML 20 cells. And we can look for the telltale signs if that's not enough. If the reflections are strong, we get standing waves, we get a rolling response in our conservation.